Howdy. Now I've gone back several slides to remind you that steps 4 and 5 are described when we introduce the enzymatic cleavage reagents trypsin, chymotrypsin, and staph protease, and the chemical cleavage reagent cyanogen bromide. And that's because we're going to go back to our stock, our sample of pure full-length polypeptide, and we're going to get a new sample of pure full-length polypeptide and use a different cleavage reagent for step 5 than what you used in step 4. And the reason is we want to send those out for sequencing by Edmonds degradation. It only takes a few rounds to get the sequence of short oligopeptides and get the information back and align the fragments, which are going to be different. Different fragments are generated by different cleavage reagents, and bootstrap our way across. So that's what I want to do in this video. Reconstructing the sequence, step 6. So we're using these two different fragmentation or cleavage reagents in steps 4 and 5. And that's because, as I showed you in the trypsin example, the fragments that you generate, the short oligopeptides, are going to be mixed together, and you will have lost their order. The order of those short oligopeptides will not be known when you send those out for sequencing. The sequence that so you need the second step in order to help gain that information back. And how will we gain that information back? We will get back the sequence analysis of both step 4, cleavage with trypsin, let's say, and step 5, cleavage with cyanogen bromide, let's say. And then we'll be able to, with the sequence of those short oligopeptides, figure out their order by their aligning the common amino acids. So here's a very simple example. The trypsin in step 4 gives us AEF SGITPK, and the other product LVGK. So they might go in that order, or they might go in the reverse order. Staph protease was used, and it gave us FSGITPK, sounds familiar, SGITPK, and LVGKAE, LVGK. So what we can do is align them. So the L's line up, the V's, etc. And then you see there's overlap between this oligopeptide and the trypsin oligopeptide over here. And the other peptide lines up like with this. And in that way, you have figured out by deduction the correct polypeptide sequence. You've got the order right. And that should be confirmed by step 3, which should have told you that you begin with L and you end with K. Now, of course, this is not a real protein. It's not even a polypeptide. It's an oligopeptide. And so you're going to get many, many, many more fragments, and the alignment is trickier. It's done automatically now by computer algorithms, but this is how it is done, by overlapping the fragments from different cleavage reactions of fresh full-length polypeptide. This is for your enrichment. This is just repeating a table of the tools that we had talked about. Here's trypsin, chymotrypsin, and then there are a few that we didn't talk about down here. The pepsin is what starts the digestion in your stomach, and that might come up in our talking again. But what this table does help me to teach you is some language. So the cis bond is the red bond here. It's the amide linkage between this amino acid and this amino acid. And they've labeled them Rn-1, the amino acid before the cis bond. Cis just means easily cut. And Rn is the amino acid after the cis bond. And then they let you know about the specificity by telling you, for example, trypsin cleaves after Rn-1, arginine, and lysine, except when Rn is pro. So proline in this RN position after the cis bond is actually interfering with the cleavage not only by trypsin, but also chymotrypsin and the other enzymatic tools that we discussed. So having a proline interferes with that cleavage. It actually also interferes with cleavage by carboxypeptidases, and you can remind yourself of where that cleaves. And that is the end of the primary structure. Nope, it isn't. We're going to talk about mass spec in the next video. I'll see you then.